You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and our very own Worth Electronic technology specialists who are going to shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast. The autumn season has settled in, which means the changing of the trees, the crisp, cool morning air, and the death of gardens in the Midwest. Now, as with every year, I was forced to uproot my dead tomato plants as they reached the end of their season. And like many people, I have a wish of growing tomatoes, peppers, and herbs all year round. In fact, at one point, I attempted to build a wall-mounted herb garden in my kitchen. But even with the accurate nutrients and the west-facing windows, the poor plants did not receive the lighting care that they needed, and their dead carcasses remain hanging on my wall to this day. But there is good news. With the advancement of technology, indoor gardening and farming is now a possibility. In fact, we even have some indoor growth chambers at Worth Electronic in Germany. These are small greenhouses built and equipped with electronic components from Worth Electronic. We have our Magic Power modules and our Horticulture LEDs in 3 very special wavelengths, and these wavelengths are specially optimized for plant needs. Greenhouse farms may not be a new technology, but with an ever-growing world population and the move towards sustainability, intensive yet highly efficient and standardized food production will increasingly become the norm in future years, opening a huge potential for new agricultural sector that incorporates the latest technology from bioscience and engineering fields. But how can researchers and personnel from these separate fields actually come together to understand the mutually dependent requirements of indoor greenhouses? Greenhouses have a very long history, reportedly from the Roman era, but they were not used for viable, intensive cultivation until around the 20th century. Nowadays, there are millions of controlled, protected plant enclosures all around the world, most of which use natural light. However, advancements in lighting, heating, watering, and control systems have allowed the construction of vast, artificially lit indoor greenhouses. These installations can produce significantly larger yields than conventional agriculture and low-tech greenhouses. There are also several other advantages. The different stages and cycles of plant development can be controlled by providing different wavelengths of light to gain greater yields or even reduce growing times. Water usage is greatly reduced due to reduced evaporation and the control of humidity and temperature in the installation. The control or even elimination of insect, fungal, or bacterial pests is also more effective because of the enclosed system. In addition, the carbon footprint of food production and supply can also be significantly reduced by building the installations close to population centers, reducing transport requirements. One of the most significant future advancements in the viability of indoor greenhouses has definitely been the advancements of LED technology. Originally, LEDs were expensive and extremely limited in their wavelengths of light they could generate. However, as advancements in their fabrication have progressed, LEDs have become the preferred solution for indoor cultivation. LEDs can now be made to emit very specific bandwidths of light while being extremely rugged and relatively small when compared to other lighting technologies. In addition, LEDs have a long life, have low voltage requirements, and do not generate as much excessive heat, making them exceptionally efficient. This will greatly reduce the operating costs of indoor greenhouses. First, let's discuss the spectral requirements of plants. Photosynthesis is the process that converts water and carbon dioxide into complex carbohydrates and oxygen using energy from light. Now, although the energy radiated by the sun that reaches the Earth's surface consists of the entire spectrum of visible light and so much more, plants only utilize specific frequencies of light for photosynthesis. These frequencies are related to the absorption characteristics of different pigments that are present within organelles called chloroplasts that are responsible for different functions of photosynthesis. The majority of these pigments absorb light in the wavelengths that correspond to the colors blue and red. This is why most leaves actually appear green, as these wavelengths are not absorbed, and carrots appear orange as they contain very little chlorophyll. The most common pigments are chlorophyll A, chlorophyll B, and carotenoids. These frequencies are called the photosynthetic active radiation, or PAR region, and are defined as 400 to 700 nanometers. Chlorophyll A is the primary photopigment, accounting for around 75% of photosynthetic activity, and has absorption peaks at around 435 nanometers and around 675 nanometers. Chlorophyll B, once thought to be an accessory photopigment, extends the range of wavelengths that can be used for photosynthesis, with absorption peaks at 460 nanometers and around 640 nanometers. Energy from these wavelengths is captured by chlorophyll B before passing it to chlorophyll A through electron spin resonance. All higher plants have these two pigments, accounting for their green color. Carotenoids have a comparatively much wider wavelength absorption range than the chlorophylls, with an absorption range of around 400 nanometers to around 510 nanometers. In addition to their accessory light harvesting function, they have a much more complex role than initially thought, protecting chlorophylls from photooxidation when light intensity is high, in the low wavelength, for example, higher energy wavelength ranges. This is why the absorption wavelengths of the carotenoids overlap with that of the chlorophylls. Additionally, phytochromes are photoreceptors, or light sensors, that regulate numerous processes such as chlorophyll synthesis. In spite of the absorbance wavelengths laying mostly outside of the PAR region, they are critical to plant development. As plants are stationary, they have evolved to respond to different frequencies and intensities of light that are available and linked to responses to growing in the shade, circadian rhythm, circannual rhythm, and weather variations. In this way, artificial light of different wavelengths can be used to orchestrate and also manipulate the growth and developmental stages of plants. These responses, which include photosynthesis rate, photomorphogenesis, or plant anatomy, phototropism, which is the direction of growth, and photonasty, non-directional changes, for example, flower openings, are all dependent on a wide variety of photoreceptors that can be particular to specific orders, families, and even genus of plants. Next, we'll talk about LEDs in horticulture. Light-emitting diodes are solid-state, light-generating components that, as we previously stated, have become and will continue to be one of the greatest drivers in the expansion of internal greenhouses due to their advantages over incandescent bulbs, fluorescent bulbs, high-pressure sodium lamps, and mercury lamps. Their main advantage stems from their ability to generate specific wavelengths of light. As we discussed in the previous chapters, plants only utilize a very limited range of wavelengths and have varying requirements at different frequencies. So it would be highly inefficient to consume electricity that generate these wavelengths if the plant will not utilize them. Therefore, manufacturers usually concentrate on LEDs with wavelengths of 660 nanometers for red and 450 nanometers for blue, usually in a rough ratio of 2:1. However, recent investigations have revealed the influences of wavelengths of light outside of the conventional red and blue. Red light, which is between 630 and 660 nanometers, is the main driver of photosynthesis and is essential for growth of stems. This wavelength also regulates flowering, dormancy, and seed germination. Blue light, between 400 and 520 nanometers, is another key wavelength for photosynthesis, but must be carefully controlled and mixed with other frequencies, as overexposure at this wavelength may inhibit growth. This wavelength has also been linked to the regulation of chlorophyll concentration, lateral bud growth, and leaf thickness. Far red light, between 720 and 740 nanometers, is in the infrared spectrum and influences germination and can reduce the flowering time of plants, but also increase stem length, again as part of the shade avoidance response. Green light, which is between 500 and 600 nanometers, was once disregarded as being unimportant to plant development, but recent studies have revealed that plants in the shade of others are particularly responsive to this wavelength as part of the shade avoidance response. And finally, UV light between 280 and 400 nanometers. It's still highly experimental in the cultivation of plants. Although this wavelength is mutagenic, some plants, such as tomatoes and lettuce, are much more resistant to these wavelengths. Some studies suggest that these wavelengths can be used as fungal control on some species. Additionally, UV light may be responsible for the generation of certain protective molecules like antioxidants and phenols, which are important for human nutrition. However, it must be remembered that every type of plant will respond differently to various combinations of light wavelength and intensity. In addition, different physical characteristics are preferred for different types of plants. For example, it is desirable for salad vegetables to have thin, light leaves for improved texture when eating, whereas in aloe vera, thick leaves are desirable to produce more latex. Regarding flowering, decorative plants need to maintain their flowers for as long a duration as possible, while in pineapples, it is optimum to inhibit the flowering process to better control the harvest period. As a result, indoor greenhouse operators and artificial light unit manufacturers are always looking for new combinations of wavelengths that are particularly catered to the light recipe of specific species and even cultivars or subspecies of plants. To meet these requirements, Worth Electronic offers the WL-SMDC Surface Mount Monocolor Ceramic LED Water Clear range of LEDs. The WL-SMDC has been expanded to include wavelengths of 450 nanometers for deep blue, 660 nanometers for hyper red, and 730 nanometers to include far red, which has been selected to match the absorption spectra of photosynthetic pigments. In addition to the existing products in the range, a diverse range of combinations is possible that can be catered to the target. As with any new application, different metrics and parameters have been developed by different organizations and companies to measure, quantify, and qualify the efficiency of artificial indoor systems. Some efforts have been made in recent years to standardize these parameters, but most notably from the American Society of Agricultural and Biological Engineering, or ASABE, who have produced several documents to identify and coordinate the use of LEDs for plant growth, with a number of standards and guidelines regarding the methods of measurements and testing to quantify energy consumption and performance characteristics. Until very recently, parameters have been based upon the human perception of light, which is biased towards the green and yellow wavelengths and against blue and red wavelengths. This is why conventional parameters such as lumens cannot be used. The most important parameters concerning LEDs in horticulture include wavelength, photosynthetically active radiation, or PAR, between 400 nanometers and 700 nanometers, photosynthetic photon flux, also known as PPF, photosynthetic photon flux density, known as PPFD, photon efficacy, wall plug efficiency, and R to B ratio. The wavelength specifies the wavelength of light emitted by the LED. The PAR is the conventionally used range of frequencies of light that is required by plants to perform photosynthesis. This number can sometimes be misleading, as all wavelengths are given equal importance for photosynthesis, although, as we've seen, red and blue are the main drivers of photosynthesis. This means the wavelengths of a green LED may fall within the PAR region, but will have a very limited effect on plant growth. And the PPF quantifies the total amount of photosynthetically active photons that are produced by LEDs each second. Although it may seem strange to an electrical engineer to quantify the output of a light source by the number of photons emitted, it must be remembered that photosynthesis is a biochemical process that can be quantified by the number of sugar molecules generated per number of photons, even though photons of different wavelengths have different energy levels. The conversion from electrical power to ppf is performed using the Planck-Einstein relation and Avogadro's number and is the sum of all photons generated in the wavelength range. ppf quantifies the total amount of photosynthetically active photons that reach the target area per second. This parameter is highly reliant upon the distance and angle from the source. This is usually measured using a quantum meter sensitive only to the PAR wavelengths. Photon efficacy is a parameter that quantifies how efficient the LED is at creating ppf per joule of electrical energy used. The wall plug efficiency is a percentage that is defined as the energy conversion efficiency, a ratio of the electrical power to the optical power, and the R to B ratio quantifies the ratio of red to blue light emitted by the LED system. In summary, the improvement in efficiency, optical power, price, and lifespan have moved LEDs from the research stage of development into an innovative, viable alternative to conventional lighting sources in the application of horticulture. Although the exact influence of wavelength ratios and the role of wavelengths outside of red and blue still needs to be investigated and understood, LEDs will continue to take market share from the other lighting sources, and they'll become the dominant in the coming years. With the release of extended WL-SMDC, Worth Electronic has LEDs to match the wavelengths that are essential for photosynthesis, in addition to any special requirements that may be required for any specific types of plant. Attached links and images are available in most podcast streaming networks. To view all links, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up Radio podcast, where each week we are seeing what's up in the world of electronics and PCBs. We'll be checking in with leading industry experts, and Worth Electronic technology specialists will shine a light on our topics, such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.